Have you ever wondered what's happening right above your head? At this very moment, tens of thousands of satellites are hurtling around Earth at terrifying speeds. We are talking about objects moving at 17,500 miles per hour, faster than any bullet, faster than any jet fighter ever built. And somehow, impossibly, they almost never collide. Think about this for a second. Imagine a city with that many vehicles on the same roads, all moving simultaneously. Crashes would be constant. The highways would be absolute chaos. But in the vacuum of space, something extraordinary is happening. Every single day, these invisible machines are providing GPS navigation on your phone, streaming weather forecasts to meteorologists, delivering internet to remote islands, and keeping global communications alive. They're doing all of this at the same time, in the same space, yet we almost never hear about crashes. Most people think the sky around Earth must be overcrowded, dangerously packed. One tiny mistake, they assume, and disaster strikes. But the reality is far more fascinating and far more complex than that. What makes this possible? The answer isn't just about technology or luck. It's about extraordinary precision, constant surveillance, physics, mathematics, and the coordinated efforts of thousands of engineers working around the clock. It's a system so sophisticated and so invisible that most of us never realize it exists. But there's a darker side to this story, a threat that's growing every single year, a threat that could someday paralyze our entire orbital infrastructure. To understand why satellites rarely crash, you first need to grasp just how impossibly vast the space around Earth really is. Most people have no concept of this scale. It's not that all satellites orbit at the same altitude. They're distributed across multiple orbital layers, each completely different from the others. The first layer, closest to Earth, is called low Earth orbit. This is where most modern satellites operate today, providing internet, observing the planet, and supporting crewed spacecraft. Low Earth orbit spans anywhere from a few hundred kilometers to nearly 2,000 kilometers above Earth's surface. That's an enormous region of space. Higher up is medium Earth orbit, where GPS satellites maintain position to guide billions of devices on the ground. And then, incredibly far away, there's geostationary orbit. Satellites there must fly nearly 36,000 kilometers up, 50 times higher than low Earth orbit. The distance between these orbital layers alone exceeds the entire height of our atmosphere. Here's the crucial point. When we talk about tens of thousands of satellites, They're not crammed into one tiny space. They're distributed across these vast regions. Even within the same orbital layer, the distances between satellites typically span tens or hundreds of kilometers. From a computer screen, they look crammed together. In reality, if you enlarged a satellite to the size of a car, the nearest satellite might still be dozens of miles away. That's like two cars on the same highway, separated by an entire city, never catching up to each other. This immense spacing is the first reason collisions remain extraordinarily rare. But space alone isn't enough protection. After all, if everything flew randomly in different directions, even vast distances wouldn't help. The real secret is that every satellite follows a precisely calculated orbit from the moment it launches. Think of space as a massive highway system. Each satellite is assigned its own lane from the beginning. These lanes aren't marked with paint. They're defined by the laws of physics and mathematical calculations of stunning precision. The critical parameters are altitude, orbital inclination, and orbital shape. Change even one of these variables, and the satellite follows an entirely different path. Two satellites at the same altitude, say 550 kilometers up, can still never meet if their orbital inclinations differ. One might pass over the equator, while another constantly flies over the polar regions. From Earth, they appear to orbit together. In reality, they're operating on different routes. Even if two orbits theoretically intersect, that doesn't mean the satellites will collide. It's like two trains running on the same railway junction, but operating on different schedules. They never reach that intersection point at the same time. The timing of when each satellite appears on its orbit is calculated with extraordinary care before launch. Once in the correct orbit, satellites maintain incredibly consistent speeds, about 7 to 8 kilometers per second in low Earth orbit. At this velocity, it takes only 90 minutes to complete one full lap around Earth, because everything moves along predictable, calculable paths. The position of each satellite becomes easy to forecast. This foundation enables computer systems worldwide to predict when two objects might approach each other too closely. If a dangerous approach is detected, an alert fires immediately. It's called a conjunction warning, sent to satellite operators before any collision threat becomes real. Networks of radar stations and telescopes distributed across multiple nations continuously track every object in space. When an object passes overhead, radar measures its distance, direction, and speed with remarkable precision. This data continuously flows to processing centers that update the orbital position of every satellite in real time. It's like forecasting the flight paths of tens of thousands of aircraft simultaneously. Except the space involved is three-dimensional and infinitely larger. Currently, tracking systems monitor tens of thousands of objects larger than about 4 inches across. For each object, computers don't just record its current position. They predict exactly where it will be in the future. Millions of calculations run continuously, searching for any pair of objects approaching each other dangerously. When projected distance falls below safe thresholds, the system generates a warning. Usually, this arrives hours, days, or even weeks in advance. Plenty of time to respond. Engineers analyze the collision risk carefully. If the probability is extremely low, the satellite continues normally to conserve precious fuel. But if risk exceeds acceptable limits, the satellite performs a small thruster burn, a tiny push that changes velocity by just a few centimeters per second. This sounds insignificant. In the weightless environment of space, that change accumulates over hours into a separation of miles or kilometers. Only a few seconds of engine fire creates the necessary safety margin. Most avoidance maneuvers happen silently and invisibly. People using GPS, satellite, internet, or weather forecasts never notice anything changes. This coordination between thousands of human engineers and powerful computing systems maintains remarkable order in space, day after day. Collisions are rare, but they do happen, and the consequences are staggering. The most famous incident occurred in 2009 between the operational Iridium 33 satellite and the defunct Cosmos RRR-Will-E date. One was still working perfectly. The other had stopped functioning years earlier, but continued flying on its original orbit. They slammed together at relative speeds exceeding 17,000 miles per hour, releasing enormous energy in seconds. There was no fireball like in movies. Oxygen doesn't exist in space to fuel flames. Instead, both satellites were ground nearly to dust into thousands of metal fragments, scattering in different directions. In mere seconds, the collision zone became an extremely dangerous debris cloud. Radar stations on Earth instantly detected thousands of new objects appearing on monitoring screens. The workload for space coordination centers skyrocketed. Every single piece of debris now required independent tracking. Even today, many fragments from that 2009 collision still orbit Earth and continue being monitored. One satellite destroyed. Hours-long collision event. But decades of consequences. One destroyed satellite increases collision risk for thousands of other operational satellites. The most terrifying danger isn't satellites that are controlled. It's the countless pieces of space debris with no one at the controls. These fragments are old rocket stages, broken satellites, and pieces created from past collisions. Some pieces are only the size of a screw, yet they travel nearly 5 miles per second around Earth. At these velocities, size becomes irrelevant. Kinetic energy is what kills. An aluminum fragment, the size of your fingertip, can puncture a satellite's hull in an instant. This is why modern spacecraft have specialized shielding against high-speed impacts. But no shield protects against objects much larger. The terrifying problem: many debris pieces are too small for radar to detect reliably. They're like invisible bullets, constantly circling Earth. Every operator faces a baseline level of collision risk from debris they cannot see. And here's the nightmare scenario scientists call Kessler Syndrome. Every collision creates thousands more debris pieces. Those pieces can hit other satellites, causing more collisions, more debris, in an escalating chain reaction. If this happens widely, Earth orbit could become essentially unusable for decades. Humanity still has time to prevent this catastrophe. Modern satellites are increasingly designed to deorbit and burn up in the atmosphere after completing their missions, rather than becoming permanent debris. Some projects are developing spacecraft specifically to collect large debris pieces already floating in space. But the debris accumulated over decades is an enormously complex problem for all nations. One careless decision today leaves consequences for satellite generations and astronauts in the future. Only in recent years has satellite launches accelerated dramatically. The reason? Massive satellite constellations providing global internet coverage. Instead of dozens of satellites, companies now plan tens of thousands, all operating simultaneously. More satellites mean exponentially greater complexity in managing space traffic. Each day, computer systems must analyze millions of potential close approaches between satellites and debris. This vastly exceeds human capacity to process manually. Artificial intelligence is becoming critical for predicting collision risks in orbit. AI can detect unusual patterns faster than humans and suggest optimal avoidance strategies. Soon, satellites themselves might exchange data, and make simple orbital adjustments independently, creating an intelligent space traffic system resembling autonomous vehicles on Earth. But this only works if all nations and companies transparently share orbital data. One group of satellites withholding information could increase risk for the entire system. This is why experts increasingly call for global space traffic rules, laws everyone follows, similar to aviation or maritime regulations. If done correctly, hundreds of thousands of satellites could operate safely without transforming orbit into a colossal junkyard. If done poorly, a few irresponsible decisions could create consequences lasting generations. When you open a map, make a phone call, or check the weather, a satellite might be silently serving you kilometers above Earth. These small machines have become essential to modern life, though we rarely see them. To maintain this network, thousands of engineers work constantly at control centers worldwide. Every precise calculation today contributes to keeping tomorrow's skies safer for all space missions. The real miracle isn't the number of satellites, it's humanity's ability to coordinate them with such order and precision. Each orbit represents physics, mathematics, and decades of accumulated aerospace experience. The decisions made today determine whether Earth's orbital space remains safe or becomes chaotic in the decades ahead. The race to conquer space is ultimately a race of technological achievement and shared responsibility for all humanity.